So we are talking about graphs of inverse functions, okay? So on your 2B.4 that says graph or inverse function, we're going to be graphing. You are the calculator, okay? You are the graphing calculator, and you're going to be the one that does the math, okay? Why? Because in 3P, it says that you need to be able to graph without a calculator. In reality, will you have a calculator most of the time? Yes, but it wants to ensure that you can do it without a handy-dandy calculator. So your notes that you picked up today, they should fold in half and make a little booklet. Okay, the other stuff that you pick up is your assignment page, and it folds and make a little booklet. The assignment page isn't due until Thursday, okay? Our assignment page is due Thursday. That's because we're going to be going over 4, 5, and 6. Part 4, 5, and part 6. But it folds. Did you pick up 2 papers? One more. There was 2 papers? You still have applesauce everywhere? You were too excited for it. All right. So everyone's good now. Everyone has their notes and their assignment. When is the assignment due? Thursday. So if you want to write a little note to yourself on it, due Thursday. We will have a quiz over it. So on Thursday, we'll have a quiz over it. And yeah, so you'll turn in your assignment. You're allowed to use your notes. Wham, bam. Thank you, ma'am. That's our last quiz grade of the 6 weeks. You hear me? All right, so let's end it on a good foot. Good note, good, you know what I mean. All right, so 2B.4, graphing inverses. So the fastest and best way, well, the fastest way to graph anything is creating a table of values, right? Creating a table of values and then plotting those points. Do y'all remember doing that before in life? Given table of values, plot the points, connect the dots, bam, you got a function, right? All right, now, what we're at now is talking about our inverses. To find the inverse graph, you're going to be switching your X and Y coordinates around. And that's going to create the inverse function, okay? We're going to draw the line Y equals X, and that's our dashed line to show that there is symmetry amongst it, hopefully. All right, so the best thing to do for us to do is to dive on in. So up first, we have the function that we were working with last week, 2 to the X. What kind of function is this? Exponential. So this is an exponential function. Okay, because it's an exponential function, we know a couple of things about it. We know that we have a horizontal asymptote at y equals 0. Okay, and then we know that it's an exponential because your variable is your power. Does that make sense? Exponential means that the variable is the power. So we're going to evaluate. Remember, when we choose numbers to plug in, we do not want super large numbers. We want small numbers close to 0. So we're going to do -2, -1, 0, 1, 2, and 3. Okay. If I'm going to substitute -2 in for X, it looks like this, 2 to the -2. If I substitute -1 in for X, it's going to be 2 to the -1. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And what are going to be my output of that? What's 2 to the -2? 1/4, 1/4. When you have 2 to the negative, I'm going to write it down here or somewhere to remind us. I don't know where to write it. We'll write here. 2 to the -2. That means that it actually belongs in the denominator. Okay. When your exponent is negative, it actually belongs in the denominator. So this is going to be 1/4. This is going to be 1/2. What's the 0 property rule? 1. Anything to the 0 power is 1. 2 to the 1 is 2. 2 to the 2, 2 squared is 4. 2 to the 3rd, or 2 cubed, is 8. So these are going to be the points that I'm going to do my roughly best job to graph, right? Is it going to be perfect? No, we all know that your teacher can't draw, but that's okay. I try every single time. So I'm going to go to 2, and I'm going to plot 1, 4. And you should be able to plot points without me. I'm going to go to 0, plot 1. I'm going to go to 1, then 2. I'm going to go to 2, then 4. I'm going to go to 3, then 8. And I'm going to do my very, very best to connect these points. Now, even if I don't, just pretend that I did. It got a little sketchy, a little wobbly. That's a curvaceous enough graph for you. Okay. Now, with the exponential, we're going to define its domain. Your domain is saying what's happening from left to right. So what's happening to this graph from left to right? And what? It goes forever to the right and forever to the left, right? So it's going to be from negative infinity to positive infinity. So negative infinity to positive infinity, which means that x can be any real number, correct? Okay. What's the range of our graph? From bottom to top, where do we start? What's our lowest y value? Almost 0. So it's almost 0. So therefore it's parentheses 0. And then it continues to infinity. Remember, asymptotes are my boundary line. I'm going to get as close as I can, but will I ever actually touch it? No. It's a parenthesis. This is an asymptote. And so this is our y. Now, if you have another color, this would be a good time to change colors or pen. Okay, now we're going to find the inverse. So the inverse means that your x's and y's are switching places. Okay, so instead of negative 2, 1, 4, we now have 1, 4, negative 2. Instead of negative 1, 1 half, we now have 1 half, negative 1. Instead of 0, 1, we have 1, 0. Instead of 1, 2, we have 2, 1. Instead of 2, 4, we have 4, 2. Instead of 3, 8, we have 8, 3. What also changes are your asymptotes. So what's the opposite of a horizontal asymptote? A vertical. So now we have a vertical boundary line, a vertical asymptote at x equals 0. Okay, so now we're going to plot those points. So I go to negative 4, and I'm going to go down to negative 1, 4, and I go down to negative 2, negative half, and I go to 1. I go to 1, and I'm at 0. I hate when my points disappear on me. I go to 2, and I'm at 1. I go to 4, and I'm at 2. 5, 6, 7, 8. I go to 8, and I'm at 3. Now my function is doing, again, pretend that this is the most curvaceous line you've ever seen. And I went through all of my points smoothly, and I never touched my asymptote. Is it a bit of denial? Maybe. But it's really hard to draw up here. Okay. Visually, we know that these two functions are inverses, not only because we switched them, but because it's reflected over our y equals x line. Your y equals x line is the imaginary line where you're at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. You get it? At your y equals x, where your y and your x are the same digit, same value. So if you look at that line, what do you notice about this? They're reflections, okay? Your inverses are going to be reflections over the y equals x line, okay? And if they do intersect, they're going to intersect on that line. So our table graph 2. Last week we talked about this. What is the opposite, the undoing of an exponential called? A log. So guess what our inverse function is called? Log. It's a logarithmic. It's a logarithmic function, okay? And when we talked about last week, going from an exponential to a log, it looks something like this. Because we took the inverse, it's going to be y to the negative 1. So y to the negative 1 equals the log base is the same as your exponential base. And what is our exponential base? 2. Our exponential base is 2. So our inverse function for our exponential of 2 to the x is going to be log base 2 to the x. What if it had been 4 to the x? What would my inverse be? Log base 4. There you go. If the base changes, then so is the inverse base changing. Does that make sense? All right. Let's talk about the domain of this function. So the domain of my inverse. What's my domain of my inverse now? From left to right. Where does it start on the left-hand side? It's greater than 0. We start at 0 and we continue to infinity. Do we ever cross 0? It's my boundary line. And what is the range of this function? What's happening from bottom to top? The bottom is doing what? It's going to keep getting smaller and smaller, which is negative infinity. And what's happening on the right-hand side? It's keep getting larger, so it's going to positive infinity. Okay? What do you notice about the domain and range of the function and its inverse? They what? They flipped, they switched. Why did they switch? They're inverses. Did we not switch our x and our y? Yeah. So if we switch our x and y's in our table, guess what's going to happen to the domain and range of our inverse? They also flip. They have to correspond to the same thing they represented before. Okay? Yes? All right. So this is tying to what we did last week. Now we're going to jump back to good old Algebra Uno. Yay, Algebra 1. Okay? What kind of function is this thing? Y equals mx plus b, your little linear function, right? This is a linear function. Back in your younger years, you graphed linear functions. What are the 2 things you need in order to graph a linear function? The slope and the y-intercept, right? Do we have that information? Yep. Can I graph my linear function without a table? Yeah. Because you have your b and your m. Your b is your y-intercept. It tells you where you're going to begin, right? So we start at 0, 1. Your slope tells you where you're going to go. We have a -3. So we're going to rise and then go to the left, right? So we're going to rise 3, 1, 2, 3, and go to the left 1. Rise 3, 1, 2, 3, go to the left. Rise 3, 1, 2, 3, and go to the left. So your slope, your rise over your run. You're changing y over you're changing x. So we count. All right. Now we're going to do our opposite. So the opposite is you're going to fall and crawl. So I'm going to this time drop 3, 1, 2, 3, and go to the right 1. 1, 2, 3, and to the right 1. 1, 2, 3, right 1. 1, 2, 3, and right 1. I did not go down 3. Yep. I see it. That's why you should plot without me. You can count without me. 1, 2, 3. Like that was not right. There we go. And now I'm going to do my very, very best to draw the world's straightest line for you. Or Mrs. Jones' version of a straight line. Okay, that is pretty legit for me. We're going to roll with it. Okay. All right. So looking at the points we plotted, we have negative 310. Yes. We have negative 27. Negative 1, 4. We have 0, 1. We have 1, negative 2. 1, negative 2. We have 2, negative 5. And we have 3, negative 8. Can I find the inverse from this and then find its equation? How do I find the inverse? I'm just going to flip them, right? I switch my x and my y. So we're going to flip. So we're at 10, negative 3. We're at 7, negative 2. We're at 4, negative 1. We're at 1, 0. Negative 2, 1. Negative 5, 2. And negative 8, 3. How do we do? And now I'm going to plot and find my line. So we're going to go to 10, negative 3. I'm going to go all the way down to 10. 1, 2, 3. I'm going to go to 7, negative 2. 9, 8, 7. 1, 2. Because I know this is linear, I can go ahead and find a pattern here, right? So rise 1, and I'm going to go left 3. Rise 1, 1, 2, 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 3. And again, I'm going to do my very, very best to draw a straight line for y'all. I one day hope that PowerPoint's installed the straight line tool. Man, who are you telling? It would be so much better if they would just put in a straight line tool, right? Why won't they? I don't know. To torture me. All right. So this is our inverse. Can I write the inverse equation here? Okay. In order to write the inverse of a linear, it's still going to be another linear, right? Which means I need a slope and a y-intercept. What is my slope? How many did I? Negative 1/3. My change in my y is 1. Yes.
Why do you use that?
Oh,
Why?
gotcha. So you choose 2 points, right? And you want to know how can you get from this point to that point. So I went down 1 and over 3. So I went down 1 and over 3. That's my slope.
I can choose whatever point that I want
You can choose any 2 points on the line and find its slope.
in the whole line.
On the whole line. It's going to always be the same. So like if I chose this one right here, down 1 and over 3, the slope is going to be constant, consistent. Okay, your y-intercept. Now, we could take a stab at what the y-intercept is, but when you don't know exactly what your y-intercept is, you have to do a little bit of math. So to do a little bit of math, you're going to choose any point from your table. I'm going to always choose zeros and ones. If you want to choose anything else besides zeros and ones, don't let me stop you. Okay, so we know that slope is y equals mx plus b, right? If I choose 1 and 0, that means that my y is 0. We already know our slope. What is our slope? Negative 1/3. And our x is going to be what? If we're using this point, x is going to be 1. What would make this a true statement? What would b have to be? B would have to be 1/3. Does that make sense? So our intercept that we're looking for is plus 1/3. And that's our equation of our inverse. Okay. So are these two reflected over the y equals x line? They are. We have that symmetry. If I was to fold it along the diagonal, they would be symmetrical. Does that make sense? All right. Okay. Talk to me. Any questions, comments, or concerns about being able to graph an exponential or linear inverse? Nobody? Easy enough? How do you feel about being human graphing calculators? But following our requirement right now, how do you feel about being human graphing calculators? Doable? Because maybe you got to show me later. All right, let's keep getting easy. Okay, can someone remind me, how do we know if a relation is a function? If your x's do not repeat, then it is a function. If your x's do repeat, then it's just a relation. So if we look right here, notice how I call this a relation. Why did I call this a relation? The twos repeat, right? So therefore, this isn't a function, it's just a relation. So we're going to find the inverse of the relation. If I want to find the inverse of this, all I'm doing is what? Swapping, right? Switching the x's and the y's. -3, 4. -1, 2.
For the whole thing.
For the whole thing, for all ordered pairs. 0, 7. 4, -1. And 10, 2. Okay. Is my inverse a function? Are there repeating x values in my inverse? Do any of the x coordinates repeat? No. So my inverse is a function. So the inverse is a function. Okay. How do you feel about being able to tell whether it's a function or not function? Can we do this? Yeah? From a table or ordered pair, can we say if it's a function or not a function? Anyone's like, no, that was too horrible. Yes.
And what happens if the numbers doesn't repeat?
If it does repeat, if it doesn't, then it's a function. So notice here that our x values didn't repeat. So now the inverse is a function. But the relation, the original wasn't a function because you're okay. Yes, someone talks to me. Oh God. Look at that, guys. All right, so here, this is what you're supposed to be working on until the bell's gonna ring about 2.5 minutes. But you have your own y, your own linear to graph. So we'll pick up here tomorrow. You'll be graphing your own linear, graphing its inverse, and writing the inverse of the function, of the linear function. Got it? All right. You're going to use example 2 as your guide.